Hi, my name is Etai, and this is our ICCV paper, Blended Point Cloud Diffusion for Localized Text-Guided Shape Editing. Editing 3D content with textual instructions is a long-standing task with many real-world applications, and as such, there is prior work. And while this work is very impressive, it typically fails in one certain type of 3D editing, and that is fine-grained localized editing. In this setting, edits are both fine-grained and confined to a certain region, with the aim of editing these specific regions while preserving as much of the input shape's identity as possible. And this is surprisingly tricky as it requires a high level of precision. And also, you need to manage two competing goals, adherence to the text prompt and identity preservation. And this is the task we deal with in our work. Formally, given an input shape in the form of a point cloud and an editing prompt, our goal is to design a method that will provide an output which both matches the text prompt and maintains as much identity as possible in terms of the input shape. And one of the major difficulties in approaching this task has to do with the quality of training data. Most supervised semantic editing methods use a dataset called ShapeDoc. This dataset is made out of thousands of shape pairs, each with a few text prompts explaining their differences. And while this can definitely be facilitated to train semantic editing models, it is ill-posed for localized editing because the shapes are very different from one another in more than one part. As such, methods trained on this dataset to perform semantic editing usually do not perform well in localized edits, as you can see here. Here you can see that while the edits are correct in terms of text, there are differences outside of the desired parts. For instance, in the middle example, there are differences outside of the seat. In the backrest, they're in the legs. And in the rightmost example, there are differences in the armrests, even though the prompt talks about the backrest. With this in mind, we make our key observation, and that is that localized editing can be thought of as an in-painting task. Specifically, if we take the input shape and mask out the part we want to edit, we could give that masked shape to an in-painting model along with the edit prompt, and we should be able to obtain an output shape which matches the text prompt within the part region and matches the input shape everywhere else. And this is good for two reasons. One is that in-painting is very well suited for diffusion models, and we want to use diffusion models as they are state-of-the-art in terms of generating content. The second reason is that it pretty much solves our data issue. If we look at a shape talk sample, while it is not well suited for localized editing, we can see that if we focus on a single difference, ignore the distractor, and use the masked version of the target as a source, we get a perfect source target text prompt triplet, which can be used to train an in-painting model. And that is exactly what we do. So we introduce in-painting, a 3D part in-painting model. And this is how we train it. Given a shape talk sample, we take the target and use an LLM as well as a part segmentation model to mask out the part we want to edit. We then give that mask shape along with the edit prompt to in-painting. And we also give it a noisy version of the target, which is the unmasked source in this case. In-painting's goal is to reconstruct the target or to denoise the noisy sample. And once it's trained, it should be able to generate new parts given the text prompt with high fidelity in a point cloud diffusion process, which looks like this. In-Painty receives the mask shape, the edit prompt, and random noise, and produces an output which matches the text prompt within the edited part region and looks exactly like the input shape everywhere else. But this is not perfect, as the edited part is very far in terms of identity to the original part. And this is not surprising as InPainty is inherently blind to the part that has been masked. We don't want that. We want something like this, something in which the edited part both matches the text and the original part. And we do this using a novel inference time algorithm. Our idea behind this algorithm is that we have one diffusion branch that does inpainting, like we've seen before, and another branch doing full shape reconstruction, just reconstructing the full shape from noise. Then, if we can find a way to merge these two branches together, we could get a shape that matches our requirements. But first, we need to find a way to reconstruct the input from noise. To do this, we slightly tweak the training procedure of inpainting. Specifically, every few training samples, we replace the target text prompt and the mask shape with a full shape and a null text prompt, and keep the goal the same. This enables InPainty to reconstruct the full shape whenever it sees the null prompt. Now that we can reconstruct the shape from noise, we can detail our inference time algorithm. Our algorithm starts with reconstruction. We do this for a few denoising steps using the null prompt and the full input shape. Then, after a few time steps, we switch to inpainting. And we start the inpainting from a noisy reconstruction sample. The later we do this in the process, the more identity is preserved. But this comes at the expense of editing freedom. So there is a balance here. When we inpaint, we also blend coordinates outside of the edited part from the reconstruction branch into the inpainting branch. This strengthens the blend and it also increases identity preservation outside of the edited part. When the process is finished, we get our output. And notice that it maintains identity even in the edited part while also adhering to the text prompt as required. Our method blended PC has achieved state-of-the-art results both in terms of edit fidelity and identity preservation. And you can check it out for yourself as our code is freely available. Thank you very much for your time.